because in previous editions we always had some train strikes, so it's part of the organization. So this, as you know, this 15th edition is organized has been organized by James Clear and myself. But unfortunately, as James some health problems, he will not be able to be present at the conference. But he really would have loved to, but he needs to rest, so he wanted to apologize for not being able to attend this conference. Also, as mentioned on the website, we are glad to announce that there will be the journal Regional Science in Urban Economics agreed to publish a special issue made of some subset of papers presented at this conference, and we would like to thank Zanin Yang and Daniel Hackman for having accepted our propositions. So we'll give you some further information in due time because we still need to discuss the details, but we'll all be keep updated on that. For the social events, so there will be a guided tour at the broadcaster, right? Which the guided tour will be 1 hour long, moreover, and this guided tour will be followed by a dinner at the restaurant L'Orangerie, which is close by the castle. You see, it's very nice. So the departure time will be 5:15 sharp, right? Okay, and the departure location will be at the main entrance of the faculty. So that's the entrance you get through. You ride through when you arrive by tram. With the entrance with the depot just over there. Okay. So and we will go there by bus. It's I think it's 45 minutes bus to go there. So that we can get at the castle at 6:30, maybe with some adjustment, and we'll have a private guided tour of the broadcast. So this is my next point. In order to guarantee that we can leave on time for the castle, I will ask just to keep on schedule, meaning the presentation will be 20 minutes long. Then we'll have some questions to discuss on, and if time remains, questions from the audience, and we can all, as always, you can use the coffee breaks just to continue the discussions. The lunch for today and tomorrow are organized in the restaurant L'Agora, which is on the other side of the lake, which is 5 minutes walk, but there will be members of the organizing committee, so Cyril Boussoudouin, just over there, just raise your hand, Malik Kerkour, there, and Denisa Banorescu will be also showing you the way to the lunch. Also, I would like to mention that this workshop couldn't have been organized without the help of the members of the scientific committee, because they have a very tough job to select the papers, because we have received many good papers, and so we would like to thank them for all the work, for the really good work they did. And also we would like to thank our sponsors, which are University of Orléans, the Faculty of Law, Economics and Management, the CNRS, the Region Centre Val de Loire, so this is the administrative regions in which we are, and also the Department of Economics for all the financial, human resource, and rules support for the organization of the workshop. And finally, we would like to thank Cécile Chamaya and Karine Nodin for the very fantastic assistance in the logistics. So, to conclude, now we start serious stuff. We wish you a successful workshop, full of interactions. And I hope future scientific collaborations. So thank you all for coming and enjoy the workshop. We start with the first session. So this will be a session on theoretical contributions in cross-section. We'll have 3 contributors, Fejin, Abhimanyu Gupta, and Paul Ehlers. So Fejin, the floor is yours for 20 minutes.
there are many popular spatial measuring models such as SAR model, SE model, and spatial learning models. So we know that for these models, the symptotic distribution and inferences are based on central limit theorem in Kotian and Kucher 2001 paper. I think for that theorem, it is proved by using martingales. However, as we look at the literature, we think that maybe we can explore more properties of the martingales. So this paper is studying how to explore the martingale structure for tests and estimation. So first for tests, we noticed that Bowen and Britton, 2011, they have a paper. They propose outer product of gradients variance with LM test for spatial dependence. The advantage of that method is that it's very easy to compute the variances, and the method is robust to unconfidential statistics. Bertaggi and Young 2013, they have a paper. They consider the statistic and the non-normative robust LM test, and also consider the OPG variance. So actually for these two papers, the OPG variance are based on the martingale property. As we read their paper, we noticed that for their paper, they only consider the following three cases. So first, they considered in the reduced SAR model, they can test for no spatial dependence, or in the reduced SE model, they can also test for spatial dependence, or in the more general SAR model, they can test for no spatial dependence and no spatial error dependence at the same time. So they cannot test, for example, they cannot test for no spatial error dependence in the presence of spatial lag dependence, or they cannot test for no spatial lag dependence in the presence of spatial error dependence. So I think partly the reason is that because for these models, if you look at the restricted estimator, the initial estimate will have asymptotic impacts on the final estimator, final test statistics. So it's not very easy to write the OPG variance for these test statistics. However, if we can actually use the CR test to avoid that problem, because we know that if we use the OPG variance, then the symptotic distribution of the initial estimate will have no impact on the test statistics. So the statistic will have the same asymptotic distribution, and we can use any Newton consistent estimator. So the advantage of any Newton consistent estimator is that we can use computationally very easy estimators. For example, the spatial 2-stage square estimators. And as usual, we can use the OPG variance, so it's easy to compute the variance. We don't need to estimate our analytical formula for the variance. So we think this is a very systematic method to derive OPG variance for tests in spatial convention models, and we can also consider test robust heteroscedasticity and non-normative. So actually we can look at those tests, LM test, OPG variance, we can look at those tests in a different way. Because if we look at them, we can see the martingale structure. Because if you look at the symptotic distribution of these tests, they are based on the martingale structure. So we can actually use the empirical likelihood to formulate the test. For example, the empirical likelihood, or more generally a class of minimum distance likelihoods, the GEL. So in particular, the method is introduced in Arvin 1991, and later a class of minimum distance estimator considered so-called generalized empirical likelihood. And for our case, actually we have martingales. So these two papers, Maitland 1995 and 2010, 2002, are considered the martingales, the EL for martingales. So they can be seen as one-time analog of time Newton likelihood function. left ratio test. So for those methods, EL and GEL, actually they have all kinds of advantages. So for example, if you consider the test, they have the same asymptotic distribution as for example, the LM test. They don't need to estimate the variances. So you don't need the LPG formula. And other advantages, for example, bottleneck connectability, and in your sense, they are uniformly most powerful. So that's for test and estimation. Because if we look at if we notice the molecular structure, we can actually formulate an estimation in the GI framework. So the advantage of this method is that it's a one-step estimator, so we don't need to estimate the variance compared to the GMM. And there are also some other advantages. So for example, they can partially remove the asymptotic bias due to the inefficient first GMM estimator. So we look at some further restricted EL estimator, and they even have more better properties. And we can also consider some tests in the EL framework. They can be used for testing invertibility or spatial dependence. Let's have a look at the test. So first, we know that if we write a very general SAR model, so this is our very popular SAR model. So if we look at the gradients and the true parameter vector, we see that each gradient or each score here, see is a linear quadratic form, like here, the linear quadratic form. So as in Cotton-Kucher 2001, we can decompose this linear quadratic form as a sum of psi and I. So psi and I, if you consider such sigma fields, then you can see that psi and I are martingale differences. So they are uncorrelated. So we can estimate the variance of Cn using this sum of squares, sum of estimated psi and I. So that's the idea of the OPG, using this form to estimate the variance of a linear quadratic form. Now we have a vector of linear quadratic form. So similarly, we can estimate the variance of this vector using the like a sum of outer products. So now let's consider the CR test. So that's like the idea of CR test. So if we consider, for example, we have a vector of parameters, we are interested in testing a subvector, whether a subvector is 0. So this is the original score. Now, if we consider our transformation of this original score, like this form, then you see that if you have an expansion, a first order Taylor expansion, then you see this term, the second term here, will disappear, right? You can't multiply this guy here, so this term will disappear. So you look at this original statistic, and this term here, you see that the asymptotic distribution of this theta 2n will have no impact on the asymptotic distribution of this statistic, right? So as long as this theta 2n hat is Rooten consistent, you see that then it will have no asymptotic impact. So we can look at this statistic instead, that we can use this statistic to construct our test. So for example, because this is the score, so we know that earlier in the last slide we can decompose this score as the sum of this is approximate Martingale differences. So we define this as psi and I, then this is also we also have some approximate Martingale differences. So our test statistic will be like this. That's the original statistic right here. this sounds great, this guy. And then the variance of this statistic can be estimated by this outer product, So you see the test will have this very simple form, very easy to compute this variance. So you will follow this chi-square is real equal to the number of restrictions. So that's the general C-alpha test, and we can formulate using the OPG formula. So that's the general case. Now, for example, if we want to consider the spatial testing for spatial dependence, now if we have the SAR model, for example, if we want to test for tau 0 equal to 0, now we have the general formula, we can get the analytical expressions. So here, we know that we need a restricted estimator. We need to have a restricted estimator when tau is equal to 0. So the restricted model will be SAR model. So if you can just consider the estimation of SAR model, because now we don't need efficient estimator. Any root and consistent estimator will be okay. So we can just use the spatial two-stage square estimator. But because this estimator is very easy to compute, so compared to the Poisson maximum manifold, so this may be computationally easier. And similarly, if we consider to test for this kappa equal to 0, then you see that the main equation, this is like the linear regression. So even though we have heteroscedasticity, we can use the OLS. So because OLS is root and consistent, so this is even easier. You don't need to estimate the spatial error model. You just need to use OLS. So it's computation is very easy. So that's the C-alpha test. Now alternatively, actually we can this is another case. So if we have unknown heteroscedasticity, so actually this is similar to Liu and Yang because they modify. So they modify the score for the SAR model such that we can still have consistent estimators. So similar to their paper, actually we can construct a test based on the modified scores. So the modification is to make the expectation of these scores to have zero mean and the true value. So we can base our test on this vector. Then similarly, we can, as for the C-alpha test, we can construct the C-alpha test and the OPG variance. So that's similar. Now, in a different way, we can consider our test in the GEL framework. So actually, we can consider a statistic like this. So that's like a non-parametric analog of the likelihood ratio, because now zeta and I, they are approximate martingale differences. So zeta and I, half zeta and I is like an observation. So you have n observations. We can consider this statistic, and rho is a function of the scalar to satisfy some properties. For example, you can normalize this rho to have first order derivative equal to -1 and so on. So you have several examples here. So that's rho function. And so for example, we have EL, this function, we have exponential tilting, we have continuous GMN. They are all some special cases of GEL. So the advantage of this statistic, as you can see, we can prove that this guy will have the same asymptotic distribution as the C-alpha test we considered. And here, we don't need to estimate the variance. We don't need the OPG. So we only need, so here we have an optimization. We need to estimate this lambda multiply. This zeta mi hat are still the estimated martingale differences. So that's the GEL test. They have the same asymptotic distribution. Now, so that's for test. We can also consider estimation in the GEL framework. So for example, here we consider a moment vector of normal vector, so this is the homoscedastic case. Then we have quadratic moments, so here some quadratic moments and linear moments. Then, because each term is like a linear quadratic form, so you can see that this moment vector as a true value can be decomposed as the sum of multiple differences, as before. So you see here I can do some decomposition. Then this Gn can be decomposed as the sum of multiple differences and the true value. So for example, if we consider Gn estimation, we can estimate the variance using the outer product formula. So this is easier to compute compared to if you use, for example, if you want to find the analytical expression for the variance, that will be complicated because it will involve third and fourth moments. So we can estimate this form, and we can also consider the estimation under heteroscedasticity. Then in that case, we only need to let this P have zero diagonals. So that will be similar. Then we can have the following GMM test, GMM estimation. So like this, we have this variance estimator and GEL. So GEL estimator, that's a saddle point problem. So first, we can fix theta. We choose lambda. That's like you multiply to maximize this term, and then you minimize this term. Then you get the GEL estimator. And here we make an assumption. Initial GMM is from this estimation. So this Jn might not be the covariance of the moment vector. So maybe it's not the best choice, this Jn. This is some traditional assumption. Then we will see that initial GMM, that's similar to the literature, have this asymptotic distribution. That's the gradients GMM, this open GMM, this open GMM, and this asymptotic distribution. GEL, we can show the consistency, and we can also show the asymptotic distribution. So you see that asymptotic distribution, that's as in the literature. Asymptotic distribution of the GEL is the same because this is a diagonal matrix. So this part is the same as this part. It's the same asymptotic variance. We have the same asymptotic distribution as the GMM, but it's a one-step estimate. So we don't need to estimate the variance. So you see, it's just an optimization. And we can also have a test. So have a test. We have joint estimate lambda theta. Then this is an over identification test. So we can use the test to test for example, homogeneity or theta dependence. And we can also look at some stochastic expansion. Then with this is similar to Louis and Smith. Louis Smith 2004. Then we can write the first order condition for GMM in this form. Then you can also have a lambda in a sense for GMM. Then for those estimators, GMM and GEL, we can expand in this form. We can have the sum of some terms with smaller and smaller orders. And then because this guy has expectation of this guy is 0, so the asymptotic bias for the estimator will be the expected value of this psi n hat. Then we look at the asymptotic bias, we can see that in general GMM has 4 terms. That's the bias of GMM. And here we have some installation for those terms, so we skip that. And then the bias of GEL, as you can see, is like this. So in particular, you see that one term, this term, BNJ, this BNJ disappears from this form. We don't have BNJ for GEL because BNJ is from the initial weighting matrix of GMM. So GEL will have, in this sense, GEL will have few terms of bias. In the IID case, in the traditional literature, you can see BNG and tilde BNG. These two are the same, and BN omega and BN tilde BN omega will also be the same. So in the traditional literature, for the IID case, these two terms will also disappear. But now because we have spatial dependence, so it's not that nice. So in general, they are not equal. So, but in a very special case, if we only consider linear moment, then the EL has better properties. So you see this term, this BNJ is removed. Actually, still BNJ. Still, we can only see BNJ is removed from the bias. So that's the theory, and we also look at some Monte Carlo. Here, I only did the Monte Carlo for estimation, and now we can see that from our design, you can see that in some cases, GMM has very large bias. You can see here, I show here, not bias. But the EL and the ET, they have very small bias compared to the GMM in these cases. So that's maybe because that's consistent with our theory. We can have smaller asymptotic bias. And heteroscedastic case, actually in this case, in my design, I see similar performance for GMM and EL or ET. So very similar bias, standard deviation, and mean square error. So that's for this design. And I haven't done the Monte Carlo for test. And a summary. So in this paper, we explore the multi-year structure which proposes the self-test, and we think this is a systematic method to derive the open invariance of test statistics. And we can also formulate the LM test and other tests using the EL or GEL framework. And this method will avoid the estimation of the covariance. And so that's the test. For estimation, we can also consider EL test or GEL test because they can avoid the first step estimation of covariance matrix compared to GMM, and they can also partially remove the high order bias of the GMM. So, but of course, we need to consider more properties of this method because we have not considered the other properties like the bottleneck correction and the power property of the test. So we have some further work to do here. That's all in my presentation.
Thank you, Craig.
Thank you. That's a very interesting topic. Very interesting papers. I just have a few comments. I don't know much about the empirical likelihood literature. So these are the questions / comments. So, all right. So you exploit the martingale structure of linear quadratic forms in the paper, and of course you ascribe this to sort of the paper you cite there is Erasure and Tufa, right? Now, I guess it goes back a bit further to the time series literature when they're looking at nonlinear statistics. So if you look at the Hall and Rayleigh kind of work from the early 80s, late 70s. So maybe you could cite that as well. A general question, so I don't know much of the EL literature. What I do know focuses on random samples. So I just wanted to know to what extent is there a precedence of applications of EL methods to models with spatial or cross-section dependence. Now, by this, I don't necessarily mean something that has a linear quadratic form structure in it you can decompose, just generally. Yi, xi prime, where yi, xi prime are not IID. Right? Because typically in this Kitamura, Susan Shenak kind of papers, this is what you see, right? That the data are IID. But I just have a curiosity about whether there is a sort of EL theory for cross-sectional dependence. And finally, I guess you answered this a bit towards the end of your talk. How would you compare your tests of spatial dependence to those already present in the literature? And in this case, I mean, you can do Monte Carlo, but also power against local alternatives, this kind of stuff. So just, but I guess this is work for the future as well. So these are just a few comments that I have, the questions on the paper.
So for the second question, so we mentioned that our method is like EL or GEL for martingales. So we just noted the theoretical papers as you see from a slide Newton, 1985, and another paper, 2002 paper.
Okay.
So I have not noted application. Actually look at the literature.
Okay.
why EL is very good and less bias. In fact, the spatial model we have bias. Is there something we can do? And in fact, we say nothing has done this literature. I think that's something new, at least a couple of years ago.
No.
For time series, I think they could have,
Yeah.
some of them.
Yeah.
I think this topic is the first time we can get it. Because it's the multiple feature and the submodel. Once you go to the linear model, something like that, I'm not sure. Because the multiple property no longer exists.
Yeah.
I think the multiple property is important, and they have found out in statistic literature, the statistician in Chicago, I think he has a paper which is called dual likelihood. They're using dual likelihood, it's a multiple feature.
I see.
So that's the
I see.
precedent
Okay.
of the multiple paper.
Okay.
Other than that,
No, because I remember talking to Tyson Kyotsu as well about it a few years ago, and I think he said the same thing, that there's not much
yeah.
planarity and spatial, and somebody should.
So here,
You guys have, so it's good.
it's a little bit, you always say the martingale.
Yeah.
The martingale, I think also, it's not really independent.
Yeah.
And so that's what they don't, in fact, cannot be really relate the EL to the matching maximum likelihood. That's not that's thing.
Yeah.
And you have to use the other, duality.
Yeah.
So that's something not exactly EL.
Mm.
Okay, thanks. Maybe a quick question for the audience?
Basically, I hear the CR text is very good, and I believe the text will be very simple, but I kind of suspect that the final sample performance will not be good. The CR text. So you're kind of ignoring variability in estimating the data too, right? So and the statistics is very simple, and that should be very effective. And maybe you can think about a way to further improve the final sample performance, either by doing the first try or maybe some kind of final sample pricing.
Yeah, that's something like.
Yeah, I think you have done the first test already, right? Since this CR test is so simple, you don't need to estimate the full model, just estimate reduce the model you need. And especially in the case of testing the spatial parameter, you basically run the simple ordinary least square. But that is very attractive. But to try to find a sample problem, you could try the critical value. That can be done.
In some cases, I do see the CR test, even better than the score test in terms of computation. You find some property that, cannot say. Because some cases, CR test turn out to be a nice formula, we can easily calculate the statistics score. In fact, not that case. But not necessarily all the cases, but some cases.
Yeah.
So it's novel. Find some.
Okay, thank you. So, now Cynthia Abimani, Victor, will present a paper about the classification testing in certain special dynamic models. So, again, the floor is yours for the conference.
Thanks, Nicola, once again for having me over to torture the audience with some stuff. Okay, so I'm going to talk about consistent specification testing in certain spatial dynamic models. So, I mean, the paper is not complete, it's also pretty notation heavy, so the way I've decided to go in this talk is to try and strip down as much of the notation as possible and basically try and explain what I'm doing, just an idea of what's happening and present some main results in 20 minutes. Okay, so here's what I do. This is the paper in a nutshell, and the aim is to develop a general asymptotic theory for basically the trinity of tests. So you've got the Lagrange multiplier, Wald, and likelihood ratio. But in a case where the number of restrictions being tested is not fixed, and it increases slowly with sample size. So that's point number one. And point number two is related to the first talk we had here. The score vector of the objective function is approximately linear quadratic in disturbances. So I'm just comparing this to another paper I have in which the score vector is not linear quadratic in disturbances, it's just linear in disturbances. So I'll explain what the two things mean when I get to the actual theory and why there is a significant difference between the two cases. And the idea behind this test is that for Q fixed restrictions, all these tests are asymptotically chi-squared with Q degrees of freedom. And what we want to do is allow Q to go to infinity with sample size. So what we do is we standardize the test statistics, and this is pretty standard way of dealing with this kind of issue. And we try to establish that the limiting distribution is standard norm. Okay, so what I'm going to do is just jump into sort of the general setup, just a few bits of notation here in what we have, and then I'm going to illustrate everything through a very familiar example using a spatial autoregressive model. Okay, so what we do is we observe a vector which we call Wi, and this could be a triangular array, so we do the double subscripting of dimension at least s plus 1, where s is the dimension of the unknown parameter vector. The estimate of that parameter vector, unrestricted over the whole sample, the parameter space is denoted by theta tilde, and the objective function is q. Alright, now what we do is we treat s as dependent on n, so it diverges to infinity as n goes to infinity, but we suppress explicit reference to this. So I'm not subscripting s with an n or anything like that, but whenever a parameter space comes up in this paper, it's of increasing dimension. And then what I'm going to do is, I have these assumptions which allow me to define these things, but basically throughout the talk I'm going to denote by little g the first derivative of the objective function, let's call that the score, and by capital H the second derivative, let's call that the Hessian, just for simplicity. And then what I'm going to do is, this is standard in sort of the testing literature. I'm going to split the parameter vector up into two pieces. So one piece is theta 1, which is of dimension q by 1. So this is what I want to do a hypothesis test on. And then you've got theta 2, which is all the rest, which I'm not doing a hypothesis test on. So whenever I have a subscript of 1, it corresponds to the bit I'm applying the null to. And when I have a subscript of 2, it's the rest. Okay, and I'm interested in testing the null hypotheses of the following type, that the Euclidean norm of these theta 1s at a 2 value is 0. Alright, and this is a general way of formulating the linear restrictions. So thetas can be transformations of some underlying parameters as usual. So this is just like a typical classical testing setup. Also, once I impose the restriction, I'm going to denote the parameter space as capital theta superscript 0. That's not very important. What's important is that the restricted estimator is denoted with a hat. Alright, so the unrestricted one is tilde, and the restricted one is a hat. Alright, so let me just jump into a model that sort of illustrates what I'm trying to do and where this thing is motivated from. Okay, so this is a spatial autoregressive model with increasing dimension. Alright, so let's start with just a standard SAR model, but instead of having the one spatial weight matrix, we have P of them. And we denote the complete parameter vector with the lambdas and the betas by theta. And in this model, S, which is the dimension of the parameter space, is P plus K. Alright, so you've got P lambdas and K betas. Now, of course, Xn may also contain spatial lags of underlying regressors. So the columns of Xn will not be independent or identically distributed in general. Of course, the Ys are not anyway, right, because they're dynamic. So what I'm trying to do is develop a theory that works for data that's not IID. Right, so I can apply it to this kind of model. Now, why am I interested in testing increasingly many restrictions? So this is something that Peter and I have motivated with in one of our papers using the following example. So there is this paper by Case in Econometrica in which these W's have a single non-zero diagonal block structure. Okay, so in such cases it's explicitly assumed that there are no spatial effects between units which are not in the same block, and it is reasonable to expect that the lambda 0I vary across blocks. Okay, so what Case does is she's looking at some kind of technology spillover in agriculture in Indonesia. She says within a village, farmers are influencing each other equally. Between villages, there is independence. On the other hand, she imposes the same lambda over the whole model. So we said, okay, what if we allow for a different lambda for each village? What happens then? What happens, as you can see, is that the parameter space increases in dimension with sample size. Now, of course, this is just one example. You could look at any sort of balanced group interaction model and come up with the same result. And this could also be a panel data spatial autoregressive model where you have block diagonality over time. Okay. All right. So, okay. Just to be more specific, there are P districts in cases model, each with n farmers. And as I said, farmers influence each other equally within districts, but are independent between. Now, of course, case, as I said, nevertheless takes the same spatial parameter for each district. So what Peter and I said was, okay, what if you let these parameters vary? Then what you've got is you've got a separate lambda 0I for each district. There are P of them. And so if you do asymptotics, as P goes to infinity, then the parameter space increases with sample size. Now, we know actually that we have to do asymptotics as P goes to infinity. Because if we don't, if you let n go to infinity, then we have this infinite asymptotics problem that Dunfay pointed out in his paper in 2004. Okay, so this problem will arise. All right. On the other hand, you might prefer a parsimonious model. Okay, and you might think that there are some reasons that some of these lambdas may be equal. Okay, so maybe some districts lie along the same river, they have the same elevation, same demographic structure, all right, and you might think the lambdas are the same in these places. So you want to have a way to be able to test this null hypothesis of either some or all of the lambdas being equal, and you do it in a theoretically consistent way. Okay, so the null hypothesis will be of the type that this vector lambda 0 is equal to some vector, so this latent I subscript p is just a vector of ones with dimension p, and c is some chosen constant. Okay, so you just want to do a test of whether all these lambdas are equal, and in particular they could be equal to 0 under the null. So this implies increasingly many restrictions as n goes to infinity. Now, what I'm going to do in this paper is I'm going to focus on a setting in which we have PNLE estimates or QNLE estimates with n fixed. Okay, so P is going to infinity, that is the number of villages is going to infinity, but the number of farmers within each village or each district is remaining fixed. And this is a particular case, so I didn't want to go too notation heavy, but the paper has a more general setup in which you have these WINs, these spatial matrices, whose elements are big O, H minus 1, but H is a bounded sequence. All right, so as opposed to H being divergent. So you can already see why I have this issue with the linear quadratic form in the derivative vector of the objective function. Now, so the S lambda is your usual I minus the sum of the lambda i's and w's. You've got your usual pseudo-maximum likelihood objective function. G is, as usual, W times Sn inverse. Okay, so that's the notation once again that was in G 2004. And once you have this notation and you define this matrix A as having all these G's multiplied by X betas when calculated together, then you can write down the derivative function of the first derivative of the objective function as this guy here, which is linear in V, but then also has this part which is quadratic in V. Alright, so this is just like the previous talk. Now, it turns out, as many of us know, that if your H is bounded, you can't ignore this bit. So if H diverges, you can put conditions that allow you to ignore this quadratic part and then just focus on the linear part. On the other hand, if H is bounded, which is the setup in this paper, you can't. Okay? Alright. Okay, now let me come to the general theory. Okay, so let me just mention at this point that the paper gives a general result, and then you can apply it to the spatial autoregressive model. Okay. Now, in this theory, we do things the following way. So whenever I have a matrix J, and I want to partition it, I put subscripts 1, 1 for the top left, Q by Q block. Alright, where Q is the number of restrictions being tested. J22 is the bottom S minus Q by S minus Q block, and the remainder is of obvious range. And if I want to partition the inverse of a matrix, I use superscripts, not subscripts. Alright, the second bit of notation fancy X superscripted with J is just this guy. Now, it doesn't matter for this talk what this is, but if you see this thing and you wonder what it is, it's just some function of blocks of J. Alright? And when I put eta upper bar and eta lower bar of J, that just denotes the largest and the smallest eigenvalues, and the smallest eigenvalues of the generic positive semi-definite matrix J. Okay, so there's 3 bits of notation here. And then I define the standardized LM, Born, and LR statistics as your usual statistics, just standardized by subtracting the asymptotic mean and dividing by the asymptotic standard deviation. Now, I apologize for all this notation at the top of the slides. I'm just going to go through it in very quick time as to what these things are. Okay, so let's start with capital Xi. Capital Xi is just the expected value of the Hessian. Then you've got capital Psi. Capital Psi is just the expected value of the outer product of the scores, covariance matrix of the scores. And that, as we know, is just the expected value of the Hessian plus these additional terms which depend on third and fourth moments, but I've not defined them here just to conserve time and space. And then script S is just what I defined as fancy X in the previous slide, but for the expected value of the Hessian, times the covariance matrix of the score, times the transpose of this fancy X defined again for the expected value of the Hessian. And when I put a hat on it, it's just the same thing evaluated at theta hat. And when I put a tilde on it, it's just the same thing evaluated at theta theta. So theta hat is the descriptive estimate, theta tilde is the undescriptive. And then you've got these test statistics which can be defined in the standard way. Okay. Now my aim is to try and establish central limit theorems for these 3 test statistics. Okay. The property that I want to establish is something that I call property C. So this is just an increasing dimension version of the familiar kind of properties we have for testing when we have a fixed number of descriptions. So what we have in that case is property number 1, under the null hypothesis, the test statistic should have a chi-square distribution with q degrees of freedom. I'm standardizing it, so my property number 1 is that I want the test statistic to have a standard normal distribution. Property number 2, that my test should have unit power asymptotically against the alternative. Again, under the alternative, right? So that's the same property here. Property number 3, the test should have non-trivial power against local alternatives. Now, in the parametric kind of setup, that's at a root n rate because you're testing a fixed number of restrictions. In my case, it will be at a q to the 1 by 4 by square root of n rate. Okay, so not 1 over root n rate, but q to the 1 by 4 divided by square root of n. And that's just because my q is diverging. Now, if q was not diverging, you just have the standard parametric setup. And what you get in the distribution in that standard parametric setup is a chi-squared distribution with q degrees of freedom, but non-central. Okay? On the other hand, what I get is a standard normal distribution, which is not centered. So this is the kind of property I want to establish for every test statistic I look at. Now, I'm describing the asymptotic behavior of these test statistics when the score vector differs negligibly from a linear quadratic function of an unobservable disturbance vector, which I assume to have independent elements with finite 8 plus chi moments. Okay? And then I've got some properties here of the regressors and the other various objects in the model. Let me skip that and let me come to the main result, which is divided into 2 theorems. So the first theorem, I'm focusing on LM here, is trying to approximate the LM test statistic by a quadratic form in linear quadratic forms. Alright? So this is the Vn here is linear in epsilon plus quadratic in epsilon. So just like your linear quadratic first derivative function in your PNLE with H bounded for spatial autoregressive models. Now this horrible looking condition, this is just appalling, right? But I can't help it. What you can do is you can check it for various conditions. Now this is quite easy to check actually. The delta is just the difference between, let's say, H and Xi. So H is the Hessian and the true value, Xi is its expected value. In the finite dimensional case, you would just establish a weak law of large numbers for every element of that matrix. Now you can't do that because the matrix has increasing dimension. So you have to establish this weak law of large numbers for the norm. Okay? And then you can do this for each of these elements quite straightforwardly actually. But you can't, if you're giving a general theorem, unfortunately, I can't, I think, avoid this kind of condition. But this is basically just a weak law of large numbers condition. And then when I do this, I can approximate the LMS statistic by a quadratic form. And then this quadratic form is now no longer a quadratic form in epsilon. Because you see, each V is itself a quadratic form in epsilon. So you've got here a quadratic form that's a quadratic form in quadratic forms. Right? Okay, so this is quite challenging, but what you can do is write this quadratic form in quadratic forms as a function of fourth moments, third moments, and second moments, and first moments, and split all of those up into martingales. Okay? So when you do that, we can establish a martingale central limit theorem and establish asymptotic normality. Now the proof is not complete, so this is, I'm sticking my neck out by saying this is a theorem. So I've done the Lyapunov condition, but not the second condition, which is to deal with the variance, because that can be quite nasty, as you can imagine when you have something with so many elements and moments. You've all over 60 terms actually. So I'm still working that out. Yeah, so okay, so that's the main result, and this is the conclusion. So I'm hoping to provide a general theory that works in a wide variety of situations. So it's not restricted only to this model that I showed you. And in cases where, yes, if you have a vector-stochasticity robust version for a fixed case, you can also extend that to an increasing dimension case. And it's very easy to apply this test, so it's tricky to explain it because of the notation, but application is easy. Ln minus q divided by square root of 15. And I'm doing some Monte Carlo and empirical example, etc. to add some color to the paper. It's pretty dry at the moment.
Okay, thank you very much.
Okay, a few comments from my side. Well, I saw the term dynamic in the title, but I think that you are dealing with higher order space and autoregressive models. And that also brings me to the second point, is what is actually the difference with the 2015 paper in the journal Econometrics that you wrote together with Peter Robinson? My impression was, but correct me if I'm wrong, that you are more focusing on maximum likelihood estimation than on IV. Maybe you should spell out a little bit better. I was a little bit in doubt about the third issue, and I was wondering what you're doing. So you can have the number of groups going to infinity, or you can have the number of people within each group going to infinity. What is actually the more interesting thing? You said something about it, but I think you should spell it out better in the paper. Maybe you should explain better as well that P represents the number of spatial lengths. And yeah, well, then why does it make sense to let P go to infinity? So the number of spatial lengths go to infinity, and you gave the example with the group interaction matrix. But in the introduction, you're also talking about a W where the elements depends on the distance, but you're talking in distance in a very general way. So also economic distance, so in terms of income levels. So I was wondering, can't you come up with an example that's a bit more related, to other daily empirical problems? Always this group interaction matrix. So you have this group interaction matrix. You let a number of groups go to infinity, but these people within the different groups can't interact with each other. But is there also an example where some way of interaction between those groups is also And then the final thing is, well, in you said, well, the parameter space is not so important. Well, I'm not so sure about this because I'm working on a paper myself with Lacan and on the parameter space and higher order space trigonometric models, and these parameter spaces are absolutely not straightforward. You can have very weird combinations, maybe not with a group interaction matrix because then the groups are interdependent of each other. But as soon as you make these groups dependent on each other, then the parameter spaces become very weird, and you really need to take that into account. Also because you are maximizing the log likelihood function, and if you take into account the Jacobian term, then all these restrictions on the parameters play an important role in defining that. These were my comments.
Yes, so let me just take the last one, just very quickly. Quick answer. So yeah, I totally agree. So I guess I didn't put it clearly enough. So what I meant was I didn't want you to focus on the parameter space in this talk. So in high dimensional models with implicitly defined estimates, there is a huge problem with this parameter space. And in fact, in my paper with Peter, we had to restrict the parameter space always to have bounded volume. Otherwise, even the compactness doesn't make sense. So yeah, so I mean, the paper is not very complete, so maybe I didn't address this well enough. So I completely take your point. I totally agree with you there. So my apologies if I did not make that point at all in the talk. But yeah, right. Do I have time to answer other stuff? Or?
We will move.
Okay, one more. Okay. All right, so maybe
The previous one.
yeah. So there's a difference with my paper with Peter. I mean, so in that paper we were looking at ONS and IP estimation, and we were looking at inference on finite dimensional subsets of the parameter space. Whereas here I'm looking at an inference on something that doesn't have a fixed dimension. And this relates to point 3. So this other paper that I mentioned in the introduction, in that we had settings in which both h and n go to infinity. And actually that makes the work much simpler because then we actually have a quadratic form in epsilon, which we can deal with, for instance, in the way that Faye was suggesting, we just write that as a martingale. But when h is bounded, and this can happen sometimes, people have data over a large number of districts or villages, but then they don't typically, in some cases, sample again in a village to expand the sample size, but they take another village or another district. I have situations like this in mind, where you have a fixed number of people within each sampling block, but then you increase the number of sampling blocks that you have. So, but it's primarily a theoretical problem, how to do a central limit theorem for a quadratic form, which is a quadratic form in quadratic form of increasing dimension, basically.
I think in your case, I think to test it, I don't see problem. But if you're talking about villages, you find a number of people, not increasing. Although the lambda I, the lambda depends on each village.
Yeah.
So I think that's impossible to estimate consistently each lambda I, because you may find a number of people in the village, across village, except a different village, different lambda. Impossible to estimate the lambda I consistently. So if I want to test, for example, what the lambda I is 0, if I do one test, I estimate consistently before I do it. You mentioned your project, the test statistic is the sum of the quadratic form. That's okay. But the question, what is the test? I mean, I see the sum of the quadratic form, the average. Sometimes the mean is still as a term normal. That's no problem, right? But each block is still quadratic form dependent.
No, that's the point.
Yeah, but the lambda, if I really want to test the lambda, you put lambda 1 equals lambda 2, etc. 1 equals 0, I think consistent estimate of lambda I.
Yeah, so what can happen is that n can go to infinity, but if it goes sufficiently slowly, then you can't neglect this second quadratic bit.
Yeah, I know that, but the question is you cannot estimate the lambda 1 and the I consistently. I cannot do one test. How can your method can do anything?
No, but you can let n, so I just use the n, so I agree, I use the n bounded thing just to fix idea, but you can let n diverge.
No, that was a different story,
Yeah, but if it doesn't diverge fast enough, the quadratic bit is still not negligible.
Yeah, I understand that, yeah, right, also depends on X,
Yeah, yeah.
whether it's ID or not, if it's IT, you know.
Exactly, yeah, exactly.
Right, that I understand, but the example, you're talking about finite number of people, really, until lambda I, I'm worried about the consistency.
Yeah,
That's
sure.
right. I don't have a testing problem with testing, you still come up some type square,
Yeah.
but what exactly are testing, you know, that's
Yeah.
something, you know, visual statistics,
Yeah.
that's what,
Okay,
Thanks.
thanks.
Thank you.
Thanks. We will turn to the last business for this session so far.
Okay.
Let's go, so,
This is about the SLX model together with some Maria Malek-Peter, she's also here, over here. And yeah, one of the main issues in spatial econometric research are spatial spillover. So what we are eventually interested in, if you change an X variable in one unit, does it affect the dependent variable in other units? Okay. Well, there are now 8 different spatial econometric models that can be used to calculate, to determine those spatial spillovers. And the differences among these models depend on the type of spatial lags that you include in your model. So you can include a spatial lag in the dependent variable, in the independent variables, and the error term or combinations of terms. And the interesting thing is that the theoretical spatial econometricians, and we saw 2 of them this morning, they always focus on the models that produce spatial spillovers that are actually quite limited. There are restrictions imposed on these spatial spillovers. Well, if you want to have them fully flexible, you should at least consider spatial lags in the independent. And if you think about it, in total, there are k plus 2 potential spatial lags that you can include in your model. And these spatial lags in the independent variables are k. So you k explanatory variables, you also have k spatial lags in the x variables. So that's the majority. So why don't we focus much more on those WX variables? Well, we go, and that's important because then the spatial spillovers are much more flexible. And another issue is that when you use the SLX model, then you can also easily parameterize the W matrix. We pointed that out in a paper that has recently appeared in the journal Regional Science. But we've only focused on this matrix, the inverse distance matrix. So every element in the W matrix was specified as 1 over d to the power gamma. And we estimated this gamma product. What we do in this paper, we consider also other specifications of the W. So we start with the SLX model, and then later I come back to these theoretical spatial econometrics. But first, the first one. So you can also consider a negative exponential function. You can also a gravity type of function. Spatial econometricians are often criticized for not paying attention to the W matrix. Well, people often say, well, this W should be embedded in economic theory. But if you look into in the literature, you see many papers explaining flow data, and the most popular model to explain flow data is the gravity time function. So you have 1 over d to the power gamma, and you also have, for example, population size in both regions that you're looking at. So why don't we work with the gravity type of function and estimate the gamma parameters of the gravity type of function when we work with a W? Another thing is, why would the spatial weight matrix the same for every variable? For example, if you have k explanatory variables, you also have k WX variables. why won't we work with a W where every W matrix is different? So we can work with 1 over d to the power gamma, but let this gamma be different from one explanatory variable to the other. Now, why is this important? Because it has a tremendous effect on the spatial spillover, which I show you on the next slide. This is an empirical example where I use the well-known cigarette demand data set of Balta. So we're looking at cigarette consumption in each state, and cigarette consumption is explained by the price of cigarettes and by the income level in each state. Now, if you look at the direct effects here, the SLX model is extremely easy because the direct effects are just equal to the coefficient. And if you look at those direct effects, no matter which W matrix we adopt, the price elasticity is always approximately -1, and the income elasticity is always approximately 0.6. So it doesn't matter which W we adopt, we always get a similar kind of result. What I suspect is that many people, when they write a paper, then they always have a sentence like, well, we tested several W specifications against each other, and we found that the results are robust to that. What I think is that they focus on the direct effects estimate. Yeah, they are robust. But the story completely changes as soon as you are looking at the spatial spillover. And that's what's happening here. So here is what happens if I use the binary contribution matrix. Here, in the SLX model, the coefficient estimates of the WX variable, W times price, W times income, the coefficient estimates are also equal to the spatial spillover. So that's easy. So here we see when we have the binary contribution matrix, the price spillover effect is negative, which is in contradiction to what you would expect. If you increase the price in the state, of cigarettes in the state, then you would expect that people start buying cigarettes in other states, in neighboring states, either legally or illegally. So the bootlegging effect. So what would you expect that the coefficient will be? That it would be positive. If you increase the price in one state, people start buying cigarettes in neighboring states. But the sign is negative, in contradiction with what you would expect. When we adopt an inverse distance matrix, where gamma is set equal to 1, so 1 over d, then the price spillover effect is still negative, but no longer significant. If we use an inverse distance matrix, estimate the gamma parameter, which is 2.9, then the price spillover effect is positive and significant, the way we expect it to be. So the way we specify the W is extremely important for the spillover effects that we obtain. When we adopt the exponential decay function, it is again positive, significant, but its magnitude declines. When we have different gammas, so here you see the gamma for the price variable is 5.9, for the income variable is 2.9, it is again significant, stronger in magnitude, but now it's only weakly significant. If we estimate the gravity type of function, so we get three delta parameters, then the price spillover effect is positive, but very small and insignificant. So what do we observe? When we adopt different W matrices, the sign, the magnitude, and the significant levels all vary across these different W's. So it's extremely crucial that we pay much more attention to how the W matrix should be specified. So all these theoretical spatial mathematicians pay more attention to the WX variables. Okay, but, and that's the second part of our paper, if we have considered WX variables, is there a reason to further extend the model with a spatial lag, either in the dependent variables so you get the spatial Durbin model, or in the error term, so you get the spatial Durbin error model. Well, what's the difference between the spatial spillover between these two models? In the first case, the spatial spillovers are global. That means if you change an X variable in one unit, it affects the dependent variable in other units, even if these two units are not connected to each other according to the W specification, even if the elements in the W are 0. When you have those spatial Durbin error model, the spillovers are local. Two units can only affect each other if the elements in the W are non-zero. Now, to figure out whether we need to use one of those, extend the SLX model to one of those models, many tests have been developed in the literature. The LM test, I answered. But the LM tests have been developed for the OLS model and comparing SAR with SEM, but not for starting with the SLX model and comparing SDM with SDBM. So I'm not so sure whether these results that they have found are also apply to this comparison. And I suspect that these tests will be less powerful because what I observe in general is that the log likelihood function values of the spatial Durbin model and the spatial Durbin error model are much closer to each other. You can also estimate the general nesting spatial model, so include all spatial lengths, but then you have problems with overfitting. So when you test, can I simplify the model to the spatial Durbin model or to the spatial Durbin error model? The answer is in general yes. So you can't separate them. Then you have the Bayesian comparison approach developed by Lesage. Extremely useful method. I've worked with it. It's fantastic. So you can test against each other, both simultaneously, the specification and the W. Then you have the J-test. The J-test. What the problem is of the J-test, that all these people working on J-test articles, they never make their code available. So for me, I don't want to program this. I mean, that's a lot of awful work. So people should make their should go and make available. Actually, I said this in my editorial to. I'm now editor at Spatial Economic Analysis. I put it in my editor. That's what you can do as an editor. By the way, we also last year was a conference in Scotland about spatial geometrics, and we are also planning a special issue based on that conference. Arnold is sitting there, knows the details, and we also are working on a special issue of this workshop last year in France. But what the problem is with all those tests is that they always are based, that they do not account for W's that are parameterized. So as soon as I parameterize the W in the SLX model, so by 1 over e to the power gamma, and I want to do something similar in, for example, the SAR model, it makes sense that this lambda of the WY term is different from the lambda of the gamma in the WX term. Well, none of these tests has ever considered that. So there is, again, a lot of work to do for all these theoretical spatial geometricians to consider those cases as well. So what can you do? You can estimate the spatial Durbin error model and the spatial Durbin model, but with the W specified, well, first as a binary contiguity method. For the SDE model, that works quite well. So let's say that you have WX variables and that you use the binary contiguity matrix, which might be specified, and W might be the true matrix, which you don't know, but you get a misspecification error which is transmitted to the error term specification, and as a result of which the W in the error term specification is different from the W which you used for the WX variables. But it is not so important because this only affects the efficiency of the parameter estimate and not its consistency. So even if it's partly misspecified, you mentioned it this morning as well, okay, that this will do? Well, there are a couple of outcomes. So now you can use, I borrowed this test, the Houseman test. You can compare SLX with SDEM estimates using a Houseman test. I used the ticket from this study. And now you have you compare the parameter estimates of the SLX model with the SDEM model. And now you can say, well, the parameter estimates are different. Then you have a misspecification problem, so it could be that relevant explanatory variables have been omitted from the model erroneously. Or they are similar, and then you might have that the spatial autocorrelation coefficient is significant or not significant. If it's not significant, the SLX model is acceptable on the data. If it is significant, you should adopt the spatial Derwent error model. That's what happened here. The spatial autocorrelation coefficient is significant, but the parameter estimates of the two models, SLX and SDEM, are not different from each other. And if you look at the spillover effects, they don't change. So that model is acceptable on the data. If you do the same trick with the spatial Derwent model, it doesn't work, because then a misspecification in the W might affect the other parameters, so you have a consistency problem. And that's exactly what happens, because now we get negative surprise spillover effect. So we thought, okay, let's also parameterize the W of the spatial lag and the dependent variable. But that's not so easy to do that, because the shape of the log likelihood function as a function of this gamma parameter takes a very weird shape. There is not a global maximum. And that's due to the fact that there is a perfect solution problem. If the gamma is equal to 0, then all the elements of the W become 1, except the diagonal elements. And then you have a W which has formally excluded by Lung-Fui Li in his 2004 econometrica paper. But that's formally. How do you do this numerically? That's a different problem. But in this case, you can see that there is an optimum here around 5, and that's the result that we obtained here. This gamma is 5.54, and if we estimate that model, the spillover effects are again, price spillover effects are again positive and significant. But then we discovered another issue. If you bootstrap those, I'm almost finished. When you bootstrap the spillovers, as we tend to do, which is necessary in the spatial Derwent model, then the question is, do you also take into account the uncertainty and this, this gamma parameter? If you ignore it, the price spillover effects are positive and significant, but if you take it into account, they become insignificant. So and that's because there is a lot of uncertainty about this gamma parameter. So you can read it in a positive and in a negative way. The positive way is say, so well, if I change the gamma parameter, so I can work with an inverse distance with gamma is 2, 3, 4, 5, or 6, it doesn't matter. The results don't change. That's the positive interpretation. But the negative one is that you say, well, I have no idea about this gamma parameter, because whatever value I keep, the log likelihood function value hardly doesn't change. And if I take that into account in the calculation of the spillovers, then they become insignificant. So, conclusion, there are a lot of things we still need to think about.
I think reference variables are a very important phenomenon. Sometimes the W matrix is very important, because if you choose different W matrix and you see that maybe the sign of spatial dependence will change. That's very interesting. So I think, but I think for that method to parameterize this W, maybe there are some problems we need to think about first, because we know that if you have different parameter gamma, then the density of this W matrix will change. But in the literature, we know that if the, in general, the denser the W matrix, the more bias we have for this estimator. So maybe if you compare the results for different gamma, then maybe because they involve different biases, then the comparison may not be fair. So that might maybe, I think, be attention to that. And so that's for, hopefully that's this one. And so that's for the case if you have consistent estimate, but if we consider the inference problem, then maybe we also need to pay attention because if you have, because when gamma is very, very small, maybe we have the conversion rate maybe pretty different. Maybe different from the root 10, just like the minimum. So then in this page 2004 paper, then in that case, we have different inference. We need to take that into account. Then if you look at only look at the standard error, maybe, and the significance may be not valid. So that's also a little bit about. So that's two. I think that's two main concerns I have. And so I think if you look at your tables, especially for the battery continuity matrix, for that one, I see very significant negative spatial dependence. Maybe that's because the matrix is specified. But for other cases, you see very insignificant spatial dependence. Insignificant negative spatial dependence or positive significant spatial dependence. So maybe that's similar enough. This matrix is severely that the matrix is seriously specified.
I agree with the last point. I've tried to demonstrate that the binary continuity matrix is indeed seriously misspecified. That appears from all the results, which is kind of worrying because this is the most popular matrix that is adopted in most empirical applications. So that is really an issue we should pay more attention to. I also agree with all the other points, especially the second one. The way I'm looking at it now is that if we have, so in our case, 1 over d to the power of gamma, I think that this gamma, and that also follows a bit from my log-liking function value, should be at least greater than a half, which has to do with this nth rate of convergence. So if you have 1 over d to the power half, then the rate of, this condition is met. If it's lower, it is not met. The way I think about it now, but I would like to, if you want, we would like to discuss this.
So one solution is to use Bayesian priors on these hyperparameters that you have for these decays and things. That way you can make sure it's greater than 1/2, and you can also, get into the situation where your likelihood function is not just run on flat and so on. So, then if you were to, you could actually estimate those things with MC sample on that, and then you would not have to bootstrap, and you have some idea of the post-query distribution for this rate of decay, how that compares with your prior, whether the data is capable of saying anything intelligent about the rate of decay. And I suspect in many cases it's not, because we are trying to estimate too much.
Now, it is important for everybody here that this problem only occurs in the W of the spatial lag in the dependent variable. For all the other variables, it's not a problem. Then it works. But that is the only term that creates lots of problems.
Maybe we could continue that during the configuration. We will not get into that. No, but just answer the question. We can have a quick break up to, let's